And now I say that we move to the next presentation from 6G-SHINE project, and it will be presented by Baldomero. So please, Baldomero, if you want to.
Thank you. Can you see my screen already?
Yes, we can.
Okay, thank you. First of all, for the invitation. My name is Baldomero Coll-Perales, and I'm with Universidad Miguel Hernández of Elche in Spain. And I'm presenting today on behalf of the 6G-SHINE project our vision on the architecture enablers that are needed for the definition of 6G subnetworks. Basically, in this presentation, I will go briefly through the 6G-SHINE vision and the definition of use cases that motivates the architecture innovation that are needed for realizing these subnetworks. I'm listing here some of the innovation that we are defining in the project, but for additional details, we will release soon a complete deliverable focus on architecture. I will finalize this presentation with the potential standardization impact of this innovation. Well, basically, the 6G-SHINE project focuses on developing technology components for 6G subnetwork, which are installed inside entities like robots, vehicle, production modules, classroom, and in some cases, replacing highly critical and sensible cables. And these subnetworks are characterized by being short range and low power cells made by elements with potential very different capabilities, like could be sensors, actuators, car PCs, or image processing units, and even for some cases, smart glasses, smartphones, or watches. And we consider the use cases that to be supported by this subnetwork to have extreme performance requirement, which need to be supported in potentially dense subnetwork scenarios. So in addition, the subnetwork design target the standalone operation, but subnetwork can also benefit from the operation from a seamless integration with a broader cellular infrastructure, the 6G parent network, for what we call the deep edge cloud continuum operation within the 6G network of networks. Importantly, to realize this vision, we have been working in 6G-SHINE on architectural innovation that are needed for the integration and the interworking of 6G subnetwork with the 6G parent network. And this architectural innovation will be the main point of my presentation today. I'm presenting first the use cases that have identified in 6G-SHINE and that motivate the design of our architecture innovation. I'm sorry, I was pointing on, and you cannot see it. We have defined use cases for 6G subnetwork in 3 different categories. In the subnetwork category, we have 4 use cases, including the immersive education, indoor interactive gaming, virtual content production, and augmented reality navigation. All these use cases form subnetworks between different set of sensors and devices, and benefit in all the use cases from the integration with the cellular infrastructure for different purpose in each use cases. And as an example of the requested KPIs in this category, you can see the communication cycles, packet sizes, delay, and scalability requirements for the immersive education use case. In the industrial subnetwork category, we have also identified 4 use cases and 1 transversal use case. In this category, the subnetwork are made by sensors and actuators that can be found on a single robot, in unit test cell, and also in swarms of robots that need to coexist. And these use cases are characterized also by the stringent requirements of industrial scenarios in terms of communication cycles, packet size, reliability, jitter, as well as density I mentioned before. For the automotive or in-vehicle category, we have considered use cases going from a subnetwork in a single zone, connecting the sensor and actuator to a zone ECU or to a high-performance computer, to scenarios that require the coordination and collaboration between subnetwork deployed in different zones. And finally, a use case that exploits the integration with the cellular infrastructure for the offloading of certain in-vehicle functions or certain computing functions to the network. In this case, the requirements come from the automotive systems like the ADAS or infotainment system that this subnetwork have to support in terms of latency, data rate, reliability, determinism, and control loop time. So the use cases define the requirements that for the integrated 6G subnetwork and cellular networks must support. And to the best of our knowledge, this cellular network today lack the necessary mechanism and architectural enablers for a flexible and seamless integration with subnetwork, which challenges then the provisioning of this demanding service level in an effective and cost-effective manner. So considering the different degrees of capabilities of the subnetwork elements as well, and considering the existing subnetwork-like solution like personal IoT and ambient IoT network, we think that they are targeting very different scopes and requirements, and then there is gap for the solutions that 6G-SHINE is proposing. We also believe that subnetwork require interfaces and mechanisms for enabling a dynamic choice of fully or partially independent operation, which are not available also today. And the existing solution actually might require the complete transfer of all subnetwork subsystem operation to the 6G parent network, which is not effective. So we envision a dynamic and functional splitting and offloading for the interworking and standalone operation of the subnetwork with the 6G parent network. And these are the main areas of research in terms of architecture in 6G-SHINE. On one hand, it's a definition of flexible subnetwork architecture that fit to the different subnetwork categories. And this includes the definition of subnetwork elements, roles, and communication modes, and flexible subnetwork deployment options. We also see critical the definition of interfaces and exposure function for the integration of the subnetwork with the 6G parent network in order to realize the deep edge cloud continuum in the network of networks. And the third area refers to the architecture enablers that are needed for allowing the integration and interworking and functional splitting between subnetwork and the 6G parent network. And finally, the enablers for the operation within the subnetwork in the unified 6G network of networks in terms of radio resource management or, for instance, computational offloading. So for the definition of a flexible subnetwork architecture that fit all the identified scenarios, we have defined a set of subnetwork elements according to their capabilities in terms of computational, communication, power, energy, and leading to this set of subnetwork elements, element with high capabilities, element with low capabilities, and basic subnetwork elements. And we have also defined families of functionalities and features that can be allocated or assigned to the subnetwork elements, including gateway functionalities for managing data traffic and routing the data, the compute offloading functionality for orchestrating and performing function offloading, the radio resource management functionality, and a key one that is the subnetwork management that allows to manage the operational activities within the subnetwork in an effective and efficient manner. And also the subnetwork architecture definition includes the communication modes and the communication relationships between the different type of elements within the subnetwork, whether they communicate directly or through another element. And this definition results in this referent agnostic subnetwork architecture, where we can see different subnetworks deployed in the same entity with potentially different topologies. And we can also see the mapping of the different roles in the different subnetwork elements for the management of the subnetwork itself, but also for the integration of the subnetwork with the 6G parent network for the interworking and for the offloading of the network functions and processing. As I said, a key element for realizing a flexible subnetwork is the management node. This is a high capability node with a management role, which can, in addition to connect to the 6G cellular infrastructure that like other high capability nodes can do, it can also act as a gateway for connecting other subnetwork nodes to the cellular infrastructure. This management node can also support functional splitting with the 6G network and take responsibility of certain management functions, including the routing of data and control information within a subnetwork, making it possible and guarantee the subnetwork operation also in case of absence of the overlay network. It is important to note also that policies and mechanisms for the identification of the management node and possibly changing this management node depending on the capabilities and willingness of the different nodes to make and to do this role are also key part of our activities. The introduction of the management node in the subnetwork also allows for definition of lighter subnetwork communication architecture. For instance, in the control plane, the management node allows the introduction of a subnetwork control plane that somehow concentrates the control plane functionalities of the elements in the subnetwork that rely on the management node, and then all the exchange communication with the cellular infrastructure is at the end made by the high capability node management capabilities. The subnetwork control plane, but also the user plane defined in the subnetwork do not necessarily need to be 3GPP standard compliant in the complete stack. And this compliance is only needed to be guaranteed in the interface between the management node and the 6G network, but not in the interface between the management node and the subnetwork nodes, like for instance, in this case, the UE. And this allows to define lighter subnetwork control plane and user planes for these subnetwork elements, and which will allow to save power and reduce complexity, which is one of the main objectives for the subnetwork operation in 6G-SHINE. Another responsibility that the management node can take is to act on behalf of other nodes in procedures like, for instance, joining or leaving a subnetwork. This will reduce a lot the signaling burden and the exchange with the cellular infrastructure, again making efficient the operation of the subnetwork and reducing the signaling costs for the subnetwork elements within the subnetwork. So this is basically done in the 6G-SHINE based on the virtual establishment of connections from subnetwork elements that are not highly capable through the a logical definition of the virtual link through a highly capable management node that acts as a let's say group member of all other subnetwork elements in the subnetwork. Another area of research in 6G-SHINE related to the architecture is the identification of enablers for ready resource management. In this particular case, for subnetwork operating in the same frequency band. And in this slide, what we want to show is that a practical example illustrating a distributed interference management scheme based on AIML for power control. In this mechanism, a high capability node can actually utilize the CSI feedback received from from the subnetwork elements in the subnetwork to actually make distributed AML-based decision on power control. And the main architectural enablers that we foresee are required for these operations are the functions at the network side that will allow this offline training of the AML model, as well as the interfaces that are needed to make this model available at the subnetwork elements for the application of this power control mechanism. Another area of ongoing research in 6G-SHINE is the utilization of ORAN for control and goal-oriented communications in subnetwork. In this case, an instance of the real-time RIC is deployed at a high capability device for the subnetwork to be able to utilize jointly application control information as well as channel state information to make a near real-time decision on specific communication resources. In the particular case of 6G-SHINE, this is done, for instance, to adjust the robot speed and trajectories based on these measurements that they can provide to the controller in order to minimize their communication interference of their communication with the high capability nodes. And finally, we are also designing an elastic orchestration and management approach where computing tags and communication links can dynamically and jointly schedule across the nodes and links that form the 6G end-to-end continuum. And to this end, we have identified three main architectural extensions which are required. The first one focuses on creating this continuum that expands the currently available network exposure functions that is basically found between the application and the network function layer. The idea would be to extend this with introducing the infrastructure layer interfaces to the network function layer to make available here the computing and the communication resources of the different elements of the end-to-end network. So by making this computing and communication continuum, the idea would be to extend also the policy control functions to exploit and to jointly exploit the communication and computing resources for the scheduling of the computational offloading. And finally, the third identified area is related to the network intelligent functions, where basically we foresee that extending them with predictions on the availability of computing and communication resources could be utilized by the policy control functions to make more advanced decisions on how to do this joint computing and communication scheduling based not only on the current available resources, but also on the knowledge of the predicted one. And here, finally, I have architecture mapping the functionalities, control functions that we have envisioned for the dynamic computational offloading, indicating the flexible deployment of these control functions through the end-to-end system in order to allow both the offloading of function from the subnetwork side to the, let's say, the 6G parent network, but also the need to do this functional splitting in the subnetwork side in order to allow the standalone operation of the subnetwork in case this computational offloading is also needed from different subnetwork at the deep edge side. Related to the standardization impact, we foresee that All these subnetwork architecture innovations, considering the timeline of the 6G-SHINE project, could target potentially release 20 and release 21. So we are still working on them, and by the end of the project, we could have a better idea of this. But we also wanted to stress that really some partner projects, project partners are really contributing to standardization, in particular to providing inputs to the definition of use cases and requirements. In this case, for the SA1, where we think that a more immediate impact on standardization could actually be achieved. And this is being done mainly through the identification of the current gaps in cellular networks that we think that with the approaches that we are defining in 6G-SHINE, we could actually fill. I think with this, I'm just on time for my slot. Thank you very much for your attention.
Thanks a lot, Baldomero. I'm checking the chat, but there is no questions. So I suggest that you check a bit later if there are no question happening, and then we can have 20-minute breaks, and we will come back together at 4 p.m. So see you in 20 minutes. Thanks a lot.